Welcome to the third lecture in the sixth module on probability theory. In the first lecture, we talked about some of the basics of probability theory, some basic concepts and definitions. And then in the second lecture, I went into how to compute some of these different probabilities. In this third lecture, I'm going to focus on contingency tables, and I'm calling this lecture Bayesian Reasoning for Dummies. And really, this lecture is based on the chapter that you read in the appendix in the Daniel Levitin book, which I think is great because it really provides us with a way to compute Bayesian probabilities in a way that doesn't involve complicated formulas. And so here's the problem. Believe it or not, Bayes' theorem is actually very useful and applicable in real life. We're faced with a lot of personal and business decisions that can be informed by conditional probabilities, where one thing is conditional on something else. That's part of life. For instance, I tested positive for condition Y. Should I take drug X? The problem, though, is that Bayesian theory is often explained in a way that makes it sound like gibberish to the average person, and so we need help. And fortunately, Daniel Levitin has provided us that help through these fourfold tables, also referred to as contingency tables. And these are really a visual and heuristic cue that enable us to organize the information that we have at hand in a table and then fill in the gaps using some basic arithmetic and logic, and then compute the conditional Bayesian probabilities. And so these tables are designed to support informed decision making. So what follows is from the appendix that you read on constructing fourfold tables in Daniel Levitin's book, The Organized Mind, a wonderful book. I've also added in some of my own comments that relate Levitin's explanation to probability theory. So let's start with this case study we saw in the appendix. You took a blood test that came back positive for the hypothetical disease bleuritis. And so the only information you have on hand is, first of all, the base rate, also known as the population prevalence for bleuritis, which is 1 in 10,000, or 0.0001. So it's pretty rare. Comment here, this base rate is what you will hear Bayesians call the prior. And so we always need the prior when we're computing probabilities. The blood test, we're also told, we know that the blood test for bleuritis is wrong 2% of the time, or in probability language 0.02. And lastly, we're told that we can take a hypothetical drug X to treat bleuritis, but it results in unwanted side effects 5% of the time. So the question is, should you take the drug or not? So step one, the first step here is let's just clarify the question. The first thing we want to know is, what is the probability that you have bleuritis given that you tested positive? So we put that in probability language there, P bleuritis given positive test, so that we can then compare this probability to the 5% probability of side effects. Now note, in real life, you also want to know more. You want to know the probabilities, but you also would want to compare the severity of the side effects of the drug to the outcome of untreated bleuritis. Okay, so step two is to set up this contingency table of test results by disease status, the 2x2 table with totals on the margins. And so my comment here is, remember, we discussed in the prior lecture this table where we're comparing the true positives and false positives, false negatives and true negatives. That's essentially what this test is, but now we're going to start filling it in with the information that we have at hand here. So first, fill in the table with information that you know. We're told that 1 in 10,000 people have bleuritis. So what you want to do is fill this in on the margins of the table. The total population here is 10,000. You could really set, well, the only thing that's important is the rate of 1 in 10,000. So you could set the population to whatever you want it to be as long as you make the rate 1 in 10,000. But 10,000 is a nice round number to work with, so we'll use that. You know that only one person in 10,000 has the disease, so you enter that at the top there. So the next step is to use information you know to fill in the gaps. Well, first of all, if 10,000 people is the total population size and only one person has bleuritis, we can easily calculate that 9,999 people do not have bleuritis, and we fill that in on the margin. So my comment here is, if you remember from the earlier lectures, not having the disease is the complement of having the disease, and that's how we can calculate it there. Well, we're also told that 2% of the test results are wrong. So what does that mean? Well, we can compute two additional parts of this table. The false negatives in the upper right-hand side. So of the one person who has the disease, if the test is wrong 2% of the time, that means 0.02 times 1, we're going to get that many false negatives. Well, when we round that, we'll put in a nice round number of 0 there for the false negatives. For the false positives, though, if 9,999 people do not have the disease, 2% of those are going to show up as false positives having the disease. So when we multiply that together and round it, we get 200 people. And so you can see we're already able to start filling in this table. And the last step of filling in the table is just using arithmetic to fill in the rest of the table. So we know if one person has the disease and 0 tested negative, then one person must have tested positive, and that's our true positive. We fill that in. We also know that if 9,999 people do not have the disease of bleuritis, and 200 people tested positive, those are our false positives, then that means that 9,799 must have tested negative. Those are our true negatives, because 9,999 minus 200 is equal to 9,799. And then lastly, we just want to sum up the totals for those who tested positive and those who tested negative. And now, based on the limited information we had, we've completely filled in the rest of the table. And so step 6 is just to compute our probability of interest. And so the question is, what's the probability of having bleuritis given the positive test? And now you can see, instead of that really complicated formula that we went through, the Bayesian formula in the last lecture, once you have this information at hand, it's pretty easy to calculate. The probability of bleuritis given a positive test is simply the number of true positives, here that's 1, divided by the total number of people who tested positive, which is the positives and the false positives. 1 divided by 201, we get 0.00497. So your odds of having bleuritis, probability of having bleuritis when you tested positive, are 0.5%, less than 1%. Another thing here you also want to note is the sensitivity of this particular test. If you'll recall, that's the true positives divided by the total of those who have the disease. So in this case, that equals 100%. The specificity of the test, probability of testing negative if you don't have bleuritis, that's the true negatives divided by the total of those who do not have the disease. So that's 9,799 divided by 9,999, which is equal to 98%. So if you test negative, 98% chance that you do not have bleuritis. So the last step is make a decision. Should you take drug X if you test positive for bleuritis? Well, your probability of having bleuritis is 0.5%. Your probability of having a side effect from the drug is 5%. So if you test positive and decide to take the drug, your probability of experiencing a side effect is many times greater than the probability that you're actually going to have the disease and thus benefit from the drug. So this probably will lead you to not take the drug. However, your decision is also going to depend on the severity of the side effect versus the outcome of bleuritis. If the outcome of bleuritis is dying and the severity of the side effect is something minor, then you're probably going to take the drug anyway. However, if the side effect is very severe, then you're probably going to take your chances given that they're pretty good, that you still don't have pleuritis and not take the drug. But at least now you're much more informed with these probabilities in making your decision.